Okay, so homework first. Did you have any difficulty with any of these, or are we ready to move on? Yeah, all right, Ryan, thanks. Of course, the last one, right? So that one's the most exciting, I think. Or is it the last one? I feel like there was another one that was even more exciting. But let's take a look at 41. So you have x, whoa, let me get this right. So we have x over radical 4 plus x squared. Welcome, thanks for coming. Okay, so this is my function, and we're supposed to use this table back here. So let's see if we can dig out what we're going to do. And so what I'm going to do is I'm going to use um, the very bottom one. So yeah, you can't see that, but here, I'll put it up on the screen, then we can compare. Just a sec. How do I do this? I'm going to add a photo. Let's use our camera. Hold on a sec. I'll just take a photo of this. It'll be fun. There. So this is an extension of the binomial theorem, and so which oddly works even when you're dealing with fractions, fractional exponents. I know you can't see it. There we go. So this is the very bottom of that table, table 1. You'll see this thing there. So this is what we're going to use. You might say, wait a minute, that thing that you have there, it's not at all like this thing here. Well, let me do a little bit of manipulation, and then we'll make it into that. So the first thing to note is the x in the numerator. As with any of these, if there's an x times a function, it's not a problem because you just multiply whatever your power series is times x, and it just increases all the exponents by 1. That's not a big deal. It's the denominator that's the problem. So here's how I'm going to do this, is I'm going to write this like this, x times 4 plus x squared to the negative 1/2 power. So the weird thing about this binomial theorem is that the binomial theorem works even when this exponent is not an integer. So this binomial theorem, normally we think of this, and maybe you don't think of it ever, but this comes from like the Pascal's triangle and everything. You know how you expand a binomial squared or binomial cubed. Anyway, so this works even if the k here is not an integer, or if it's a negative number. You can still use this expression here. So that's what we're going to do. We're just going to force this to work. What is it that we're supposed to do? Hold on a sec. We are supposed to find, hold on a minute. Oh, yeah, just find the Maclaurin series. So let's do it. So what this tells me is that I'm going to start with x. Oh, yeah, that's this x right here. Okay, now I'll do this one at a time. Oh, the k here, by the way, k is negative 1/2. Oh, but I need a 1 there. Drat. Just a minute. I need to do a little bit more manipulation before I can do this. So I need to make this look, you know the drill with the 1 over 1 minus x thing. You would have to do some algebra to make it look like this. So I'm going to have to do a little bit more algebra. So I got a little bit over my skis, I suppose. Let's just move this over, and we will do this right. You know what? I don't even like that. I'm just going to get rid of it altogether. I know. Yeah, we will have that k, though. Don't worry. Okay, so let's try again. First thing I want to do is I want to factor out 4, and that's going to put a 2 out here. This is going to be the square root of 1 plus x squared over 4. So if you don't believe me, I'll just explain the algebra. 2 squared is 4. And then when you multiply 4 times 1, you get 4. When you multiply 4 times this, you get x squared. So a little bit of algebra there. Now I can write it like this. X over 2 times 1 plus x over 4, x squared over 4 to the negative 1/2. Okay, so k here is negative 1/2. And instead of x, I'm going to have x squared over 4. So notice that the difference between what's over here, which you can hardly see because of the contrast is bad, but the difference between this And that is that the k is different and the x, I'm not going to write x equals x squared over 4 because that seems silly, but that is going to take the place of x right here. So let's go ahead and write this out. So I have x times 1. So now I'm going to copy everything down that's right here. So I've got the 1, and then k times x. So this is going to be negative 1/2 times x plus negative 1/2 times negative 3/2 over 2 factorial times, oh, sorry, the x changed as well, didn't it? Times x squared over 4 squared. And then you've got negative 1/2, negative 3/2, negative 5/2, all over 3 factorial times x squared over 4 to the third. And that goes on. We'll get this radius of convergence business in a minute. But first, let's see if we can sort this out a little bit better. So the main thing is that we've got a bunch of 2's. It looks like there's an alternating thing here. So let's see if I can work this out. And if I can't, I'll just go to the back of the book. Or you can go to the back of the book to get it sorted out, because it may be that just I can't do it on the fly here, but we'll do our best. So first things first, we have a negative 1. N goes from 0 to infinity, negative 1 to the n. So you can see that clearly mapped out there. The next thing to note is that there is going to be a 1/2 to the n. Now hold on a minute, we're not done yet. So this is the, so notice that this is, there's 1/2 here. This is 1/2 times, I know it's 3/2. We'll get the 3 there. We'll deal with the 3 in a minute. But so 1/2, this is 1/2 times 1/2. Here's 1/2 times 1/2 times 1/2. I'm just dealing with the denominator. Maybe I should be clear about this by doing it like this. I'll do this. So the 2 to the n in the denominator. In the numerator, this is a little bit more complicated. So I'm going to have to use some trickery to get this one done. In fact, I'm just going to leave it like that for now, and I'll deal with the numerator over here. I know it seems kind of silly, put a second fraction. We'll get there in a sec. First off, let's do this. This is going to be x squared over 4 to the n. Okay, so the only thing that I haven't dealt with, I'll highlight the stuff I haven't dealt with. And I know the 1 there, whatever, but here, it's those numbers. So what I want is I'd like to have my, when n equals 1, I want this to be 1. When n equals 2, I want this to be 1 times 3. When n equals 3, 1 times 3 times 5. And so to do that, let's see if I can make this happen. I think what I'm going to do is I'm going to have 2, whoa, highlight still, just a sec. I'll do 2n minus 1 factorial. Give me a sec, let me see if that works. So when n equals 3, that would be 6 factorial. When n equals 2, that's 4 factorial. Wait, 2n minus 1. When n equals 3, that's 5 factorial. Yeah, this is good. Now I just have to filter out all of the even things. So to filter out the even stuff, what I'll do is I'll do this. I divide this by, give me a sec here, I just have to do a little bit of math in my head, n factorial times 2 to the n. Okay, so that'll do it, I believe. I know that's super complicated, but so let's explain. I'll just take this one just to show you that, oh, and I forgot my, oh, I've got that. I need another 3 factorial, just a minute. This is all times 1 over 3 n factorial. Okay. Okay, so let's take this one just to illustrate where all of my junk came from. So first of all, the negative 1 to the n, hopefully you can figure that one out. That's because I got a bunch of negatives up there. Okay, so let me highlight one at a, or no, we'll just plug in n equals 3 just to show you. N equals 3 just to show you. So this will be negative 1 to the third times 1 over 2 to the third. Now here's the tricky one. This is 5 factorial over 3 factorial times, I just realized I've got an error here, times 2 to the third. Yeah, I have to make them, see, it's a good thing I checked. So let's get rid of that minus 1 up there. There we go. Then this becomes 6 factorial over 3 factorial times 2 to the third. And then the rest of this is probably fine. 1 over n factorial, which is 3 factorial. Okay. Now we want to check to make sure that this is the same. So let's double check. When I get done with this, this is going to be 6 times 5 times 4 times 3 times 2 times 1. Obviously, this 1 over 8, that one is fine. And then this is going to be a negative. But it's this middle thing, this factorial business. So this is 3 times 2 times 1 times 2 times 2 times 2. So here's how I was clever about this. I've got this set up so that the 6 will cancel with this 3 and this 2. The 4 cancels with this 2 and this 2. And that 2 cancels with the 1 and the 2, which leaves me with 5 times 3 times 1, which is what I wanted up here at the beginning. Whew. So I think the rest of this is good, though, because I've got my 3 2's. Those are right there. And the 3 factorial is right here, 1 over 3 factorial. So I'm sure I could clean this up more, but I'm happy the way it is because, hey, I've got all my stuff. Oh, yeah, I guess I want to lump this in. So the final answer is going to be some nasty expression with a bunch of n's times x to the 2n plus 1, because you have x to the 2 in there and you have an extra x there. Multiply it all through. I'm sure the back of the book has something similar. It might not be quite as complicated as mine. Probably they combined the 2 to the n stuff. But yeah, so this is super hard. Super hard. Super hard. Not on test. Not on final. What will be on the final, you might wonder? Well, what else do you have? Questions? I'll let you know if the next one is on the final. What do you think, Daniel?
I was just going to ask why are you multiplying by x instead of x over 2?
Hold on a sec. Okay, so, because I forgot the 2. Thank you. X over 2, which x over 2. Which would give me an extra, so that would be, okay, so now I got to actually write it out. Okay, so this is going to be negative 1 to the n over 2 to the 2n plus 1. Okay, so where'd the 2n plus 1 come from? Here's n, here's another n, and then here's the extra 2. So 2n plus 1, and then this will be 2n factorial over n factorial, n factorial. Oh, fascinating. Oh, super cool. This is actually 2n choose n. 2n plus 1. Okay, I'm glad you made me do that. Okay, so that's what probably the back of the book has. It probably starts at 1. Is there a problem with, no, I think starting at 0 would be fine. So, well, there it is, something like that. I don't know if is this the back of the book? What number is this? I forgot. This is 41. Yeah, it is the back of the book. Yeah. So did anyone look in the back, or I don't have my back because I just have chapter 11 here. Did anyone do that? Look in the back? Is it at all similar to what I have? You're not going to bother? Okay, that's fine. If you don't care, I don't care either. I'm going to just say that this is correct and be done. So was there anything else? Because this one is super hard, not on final. So there are others that we can look at that are going to be on the final. And if you don't have one, I have one on the quiz that will be similar to the final. What do you think, Eli? 38? Is that one super hard as well? Let's see. No, that one's easy. Let's do 38. 38 is similar to final land here. So 38 is a good one. So this is e to the 3x minus e to the 2x. This one is good. Not hard. Maybe. Final. Okay, so there we go. So don't, yeah, this one, 41, super hard, not on final. This one, hey, it's not too hard. It might be on the final. So what we're going to look at, I won't take a picture of it because this one's an easy one. You might have it memorized by now. It's the second one on the list on this table here, the e to the x. It's the second easiest of the power series. The easiest power series is, of course, the one we've been using all along, the geometric power series. This one, second easiest, not too bad. I'll write it down here, and that is e to the x is equal to this sum, where n goes from 0 to infinity, of x to the n over n factorial. So you can see that it's not quite as simple as the geometric power series, but it's pretty close. This, oh, we never dealt with radius of convergence with 41. That's okay, it's super hard. This one, the radius of convergence is infinity, which means it converges. That power series converges for all values of x. Doesn't matter what you plug in, you can converge. So let's deal with this. The big difference here is that you have two exponentials, and instead of having x, I have 3x. Well, let's go ahead and do that. This is going to look like this. 3x to the n over n factorial. And then this one is sort of similar, but it instead has 2x instead of x. And so let's go ahead and just modify our power series. 2x to the n. So far, so good. So we're in good shape. You're almost done at this point because look at this. We've got a nice power series here. Let's just combine these into a single power series. It's not too bad. So here, I'll do it like this. Since power series are just a bunch of additions, you're summing these, you're adding these things together, you can jumble them up. You can use the commutative law, the associative law, and so on. So I'm just going to combine these like this. So I have 3 to the n, x to the n over n factorial minus 2 to the n, x to the n over n factorial. So I did two things there. I combined them into a single sum, and I used the, what would that be called? It's not really the distributive law, but whatever you call that with exponents, some algebra. Now we're almost done. Let's just factor out the x to the n, and then we'll be all set. So this goes in from 0 to the infinity, 3 to the n minus 2 to the n over n factorial times x to the n. So that's our goal. Our goal is always going to be to come up with something where the x is all by itself. And so here the x is all by itself, and then you have some coefficient. This is the power that you're going to, or the coefficient for the x. So that look all right? Did we do it? We did it. All right, so anything else to that? Oh, Eli, you're the one. Good, good. Yeah, and as far as, does it ask for radius of convergence? I think it does. Blah, blah, blah. It's there somewhere. I can't find it. But yeah, the radius of convergence would be infinite because you're starting out with something that is infinite. Up here, you might say, okay, where does this thing converge? Okay, I got to look it up now. Hold on a sec. Where's that table? I think this doesn't converge. I think this radius is 1. Yeah. So this one oh yeah, it's right there. So we're starting off with a radius of convergence of 1, which means that x squared over 4 has to be, well, the absolute value has to be less than 1. It's similar to your geometric power series. And so you would solve this. X squared is whatever is less than 1, or 2, sorry. Why am I doing 2? I know it's 4. I'm getting ahead of myself. So between 2 and -2 is where x squared will be less than 4. So that would be radius is 2. All right, let's give it a go with this. I've got two problems for you to, actually I've got 2 sets of problems. So the first one is kind of a surprise to you, but see if you can do it. So you'll see the matching. So there's a matching. If you don't get it right, you're not going to get the bottom part right. So pause for a minute, do the matching, and then check your work. I'll put it up on the screen in just a minute, and then we'll do the other part. So you'll see there's 2 parts. the matching first. Give it a go. If you can match them up, great. If you can't, then just wait for a sec until I can, here, just take them all and pass them back. Here's some. Don't worry, I'll come back to you. There's 3. I'll give you one more. Okay, here's 3. I will, oh no, there's 4 here. Amazing. There you go. So you got, good. Everyone got one. Okay, everyone got one. Is everyone here but one person? Did I ever do the recording? I did. Okay, so let's see. So here's the part. This is what I'm saying is do those first. See if you can match them up. I'll give you a minute. I'll match them up myself, and then I'll show you my answers once I get mine matched up. Ooh, here. I just realized I've got mine matched up, but I realized I need to explain how you would do this yourself. So I've got them unmatched now. Okay, so let's see how you did. So what I would do if this were on the final, which I haven't got the final quite written yet, so I don't know if this will be on the final, but if this were, here's what my strategy is. You know that bottom one? The bottom one is E for sure, because that's your geometric power series, so you should be able to match that one. And then work your way backwards. We just talked about letter C, which is number 4, so you should get that one as well. As far as sine and cosine go, just remember that sine is an odd function and cosine is an even function. So match these two up. Cosine is the one with all the even terms, and sine is the one with all the odd terms. So that matches those two up. And by the way, those are it's basically all of the terms from the exponential function that are even or odd. That's what you have there. So as far as these last two go, the way that I would suggest is to, I don't know, how am I gonna, I mean, I know which is which. I'm just trying to think of how you might match these two up. So we're dealing with D and F. So natural log, let me think about this. How about this? Natural log of, oh, I know. No, that doesn't help you. So I'm trying to think of what might help you with this. Yeah, natural log of, if you plug x equals -1 in here, the natural log of 0 is undefined. But if you plug -1 in here, the arctangent of -1 is defined. It's pi over 4. So let's see. Can I plug -1? If I plug -1 into this, I get undefined because you end up with the harmonic power series. You can check. Whereas if you plug -1 into here, I don't know, what do you get? That's a weird one. Yeah. Well, anyway, that one's arctangent. How's that? Okay, so D is arctangent and F is the natural log. So there you go. So bad CFE, whatever that stands for. So now that you got those sorted out, now you can go do these. And it's, basically, the drill is you're going to take these up here. So take the sine, which is this one, and modify it to fit that. And same thing goes with this one, the arctan, which is there. So there, I'll leave that up there. Okay, so hopefully you got something down for these. Let's see where we are. Here's mine. So the first one involved the sine. So this is the sine curve here, the exponential. Is that this? Oh no, it's the arctangent. What's the second one? So that'll be this one. So basically, I just had to sort things out in terms of. So I had a 3x. There, I'll just zoom in. You can see. Yeah, is that good? Yeah, that's really big. Just a minute. Okay, so the 3x to the fifth is out in front of my summation. I've got my summation, and then I've just copied everything down and replaced the x up above with 5x because that was my argument of sine of 5x. So that's what this looks like so far. And then we want to clean this up some. You don't have to clean it up much. Basically, the main thing you want to do is get all the x's and move the x's over to the right, and all the ins and all that stuff, leave it in one big clump. So if yours doesn't look identical to mine, just make sure that the x's are all next to each other like this. Oh, here, I'll zoom out a bit. Okay, there it is. So let me explain where everything came from. The -1 to the n, of course, is there. This 5 to the 2n plus 1 came from here. The 3, it came from the 3 out here. The 2n plus 1 factorial, obviously. And then this, it came from the fact that we have x to the 2n plus 1 times x to the fifth. So I have an additional 5 factors of x. So that's what I mean, is lump all the x's together. Now, I got a little excited when I saw this, and I thought I could make it look better. But what I did made it look worse, I think. You be the judge, though. This is great. But then here's what I was looking at, is I was like, hey, 5 to the 2n plus 1, couldn't I take one of those 5s and put it with this 3, and then maybe do something with the 2n, which I did, and that's what I ended up with. It's the same thing. It's just, I don't know. I think that that's actually uglier. That's probably better. But whatever, this is similar in the sense that you have all the numbers, and then you have the letters. By the way, I did the same thing, tried to simplify the next one, and it actually does look better. You'll see. Okay, for this one, we're using the arctangent. And so here, if you compare what's up above, I don't know, I don't have one now. But if you compare that chart, so the 2x cubed, leave alone. And then the chart says you use -1 to the n times x to the 2n plus 1, but I don't have x here. I have 4x to the fifth. So just change that to 4x to the fifth to the 2n plus 1, divided by 2n plus 1. So far, so good. So then I wanted to get all of the x's by themselves. So here I'll do another explainer. So first off, the -1, obviously. Then the 4 to the 2n plus 1 is here. And then I put the 2 in there with it. The 2n plus 1 in the denominator is fine. And then here, this is from, it's from a mistake. Here, let's fix that. Yeah, ignore that. Okay, so let's go through. Make sure I've got x to the fifth to the 2n plus 1, which is x to the 10n plus 5 times x to the third. So that's x to the 10n plus 8, I believe. Is that right? So 5 times this is 10n plus 5, and then add in an additional 3 factors of x. Whew. Caught myself just before submitting it, so I'm doing okay. And then I'm going to have to fix this down below as well. But like I said, I got excited about all the 2's. And so to clean things up, I thought it would be cool to take this and change this to 2. 2 to the second to the 2n plus 1, which is 2 to the 4n plus 2. And then combine it with that. Once again, this is unnecessary. If you have this, you're doing great. There we go. We got a little smiley face. But here I'll fix this. Let's see, get rid of that. This should be 10n plus 8. But I just lumped all the 2's together because this is really 2 squared. So I just thought that would be cool, but it's unnecessary. So anything like this, anything where you have something times all the x's, you'll be good. Okay. Whew. Let's do this. We got a couple days left, and then we're all done. Someone asked me about the practice final in the last class and in this class, I think. Yeah, I've got a. I couldn't find a good practice final, so I put on our Moodle page. I put the final I gave last year. I figure, well, that's probably close to what I'll do this year. I haven't got yours written up yet, so no guarantee, but I will have it by next Monday for sure, probably by Friday. We will see. Just a minute. What am I doing here? This is what I want. Taylor polynomials. I know it says numerical methods. I'm just cheating. I didn't want to have to. Okay, there we go. I didn't want to have to retype a bunch of stuff, so I took my notes from a different class. But okay, so Taylor polynomials. What are we doing? We're approximating. Oh, I'll give you all. Everyone did 100, right? 100, except for who's not here. Okay, so I'll make sure I do that before I leave. I did it in statistics, so those of you who are double dipping, I've already done it for stats. You just make sure that I get started on it here. Okay, so Taylor polynomials. You know about the Taylor. This is. I know it's a J instead of an N. Just overlook that for a minute. So this is the Taylor series. Taylor series for f of x, where the center is equal to x0. I think our book uses a. Does it use a for the center? Whatever it uses, it's fine. Taylor polynomial, yeah, they use a. I've got x sub 0 here, but it's the same idea. The only annoying thing here is this j. So instead of in, I have a j. I had to choose something other than in because of what I'm going to show you here in just a sec. So I could have used k, I suppose. I is a little confusing because of the imaginary numbers, but j is fine. So basically, that's what this is, Taylor series. That's all this is. So this here is the jth derivative. But you're familiar with this. You've used it a few times, so it shouldn't be too much of a shock. So that's what a Taylor polynomial is. Oh, no, that's the Taylor series. Sorry, Taylor series. Taylor polynomial is when we decide that it would take too long to add up everything up to infinity. We don't have enough time, at least not in this lifetime. So instead of adding up to infinity, we're going to stop at n. That's why I had to have an n somewhere. So I'm going to stop at n. Notice it's exactly the same expression, only I'm going to stop after when I get sick of adding things up. Now here's the thing. I'd like to know how close I am to the truth if I do this. Let me just give you an example here. Let's say that I have, I'm going to do e to the, let's do e to the 1/2 power. E to the 1/2 power using the Maclaurin series. So we'll use the Maclaurin series for this. This will be, so it'll be this. N goes from 0 to infinity of 1/2 to the, I'll use j over j factorial, even though j does look a little ugly, doesn't it? Well, anyway, so here's how this works. 1/2 to the 0 power over 0 factorial plus 1/2 to the first power over 1 factorial plus 1/2 to the second power over 2 factorial. Let's keep a running total here. Let's see. So here's what we're going to do, though, is we're going to get sick of writing very quickly here. That's supposed to be a 1/2, my bad. So what's that going to be, 1/48? Let's see, and then we'll do 1/2 to the third power, fourth power over 4 factorial. Surely these numbers are getting so small that they don't matter. In fact, can I even do this in my head? 1/2 to the fourth is 1 over 16 times 24. 16 times 24, can't do that one in my head. 16 times 24. Probably I could, I just was too lazy to. 384. So this is 1 over 384. I'm tired of adding these up. And so I'm going to stop there. And so technically what I've done here is I have computed the fourth Taylor polynomial, evaluated at 1/2. So instead of going all the way to infinity, I'm going to just get the fourth one. So let's add these up and see how close we are to the truth. Give me a sec here. 1 plus 1/2. It's going to take a minute. 1/8, 1 over 48, and 1 over 384. So I've got 1.648. 4375. So how close is that to the truth? Did I lose? How much did I lose by stopping there and not going all the way to infinity? Well, we can actually check on our calculators because our calculators has a built-in function, e to the 1/2 power. And when I do e to the 1/2 power, I get this. So here's the actual, here's the truth. I'll put up here is 1.64872. You know, I did pretty well. I mean, I'm pretty good. I'm good up until the 10,000ths place. I'm off by just 3 10,000ths. That's how close I am. That's pretty close. Pretty close. Well, I'd like to be able to predict exactly how close. Well, maybe not exactly, but can I predict before I actually do that, can I predict how close I'm going to be? And that's the goal today, is to take this thing and say, what is the harm in chopping this off after the 4th term or the 5th term or the 6th term? What is the harm? Well, to answer that question, we have to remind ourselves of a theorem that you probably have forgotten about from Calculus 1, and that is the mean value theorem. The mean value theorem says that if you have a function that is continuous, this is probably about what it says in your book if you go back to chapter 3. If you have a function that's continuous and differentiable, then there exists some point between a and b where f prime of c is equal to the slope of the secant line between a and b. So just to remind you what this means, you probably don't remember this, but here it is. So you've got a function like this, that's f of x, and then I'm going to put 2 points on that function. Here is the first point, here is the second point. So that's going to be a, this is going to be b. So let's connect the dots. So the slope of that line is this right here. That's the slope, right? Now, what the mean value theorem says is it says that somewhere, in fact, in this case, it's 2 places, there is going to be at least one place in between A and B. In this case, there are 2 such places where the slope of the function matches that slope of the secant line. Now, back in the Calc 1, when you learned about the mean value theorem, it probably went in one ear and out the other because it's pretty useless back in Calc 1. It's just something that you learn and then you forget about, which is totally understandable, to be honest. I probably did the same thing the first time I learned it. But the mean value theorem is super useful to help us to answer questions like the one that I want to answer back here, that question. So how is this thing going to be useful? Well, here's how it's useful, is let me replace some of these letters. So instead of having B and A, well, I'll leave the A. I'm going to change the B to X. So let's just change a few of the letters. Whoops, that's no good. Hold on a minute. Let me go back to some color that you can actually see. So here's how we'll do it. We'll say that f prime of c, so there exists some c, so some value of c. That notice that it's going to be somewhere, we don't know where it is, somewhere in between. That's the key. So f prime of c, c is some special number that we don't know about, is going to equal f of x, I'm going to call, minus f of a over x minus a. Now let me rearrange this. At first this is going to, you're like, what in the world are you doing here, buddy? well, here's what I'm doing. I'm going to rearrange this slightly, solve for f of x. So f of c times x minus a is equal to f of x minus f of a. There's a reason why I'm doing this. F of x is equal to f of a plus f prime of c times x minus a. Okay, so this is just a rearrangement of the mean value theorem. So here's the deal. The mean value theorem guarantees that if you pick a value of x, any x you'd like, the function value at x, the function value to x will be equal to the function value at a plus some error here, and the error will be equal to the slope at some point between a and b, or a and x in this case. I'm changing the b to x for reasons that will become clear in a minute. So you have the slope at some point between those times x minus a. This should look suspiciously familiar. Here's why is, whoops, if I can just go back one, is that you have here f, if you imagine what's going on here, you have f of x0. Here, let's just write this out. So this is f of x0 plus f prime at x0 times x minus x0. So take a look at that, and then take a look at this. They look suspiciously similar. Going back, there's that one up there. In fact, it's basically the same expression. The only difference is instead of having f prime of a, which is what we've had in our textbook, you have f prime of c. What is c? C is some number between a and b, or a and x. Anyway, this gives us a way of approximating the error. This is an approximation of the error in using f of a instead of f of x. So this is an approximation of how far f of x is from f of a. That still doesn't answer the question that I really want to answer, which is, how close am I now to the truth? But it gets us closer to that answer. So here's the deal. Without going through another page of expressions in algebra, which I know everyone wants me to do, but I'm looking at the clock thinking I don't have time to do another page of more algebra, you could extend this doing the derivative. If I did the derivative here, I would do the derivative here, and I would do the derivative here, and I would do something with this. So anyway, if you can imagine doing derivatives and then other derivatives, then you could arrive at this formula. So, and I know, oh, before you get scared. So the C here is what we typically use to represent the mean value theorem, number in here. But of course, because mathematicians, we need to have yet another letter for what we're about to do with Taylor series. And so instead of using C, we use a Greek letter that sounds kind of like C. So what Greek letter could we come up with that sounds, oh, I know, Xi. How about that one? So the Greek letter Xi looks like a little tornado. So if you draw a little tornado, that's the Greek letter Xi. So there, is that it? Anyway, here. There, that's how you pronounce it. So that letter there, we're going to use that instead of C, because of course we can't use a normal letter when we're doing something as important as a Taylor polynomial. Okay, so let me explain where this came from. Back here, this is one way of approximating how far f of a is away from f of x. Here, this is the way we approximate how far this is away from f of x. So how far are these apart? Well, this is what we're going to use. So notice, basically, this is just the next term of the Taylor polynomial, but it's evaluated at this thing here. Now that Xi, that little tornado, I know it, whatever it is, that thing is going to, whoops, I didn't leave myself enough room. It's going to be a number. Oh, I should have left it there. well, I'm going to put it right back where I had it. That is between x and x0. Or in our text, it would be between x and a, whatever your center is. Let's demonstrate this so that you see how this works. So getting back to the problem that we did just a minute ago, this one, not that one, this one. I don't have enough room for this, but not to worry. Let me point out the important things here is this, n is equal to 4, right? N equals 4. The other thing that I need to note is that x is equal to 1/2 because I'm plugging 1/2 in for x. So those are the two important things. N equals 4, x equals 1/2. Now let's go over here where I have infinite amount of room. N equals 4, x equals 1/2, e to the x is what we're using. And we're going to use the Taylor polynomial, the fourth Taylor polynomial, which is going to be this one, x to the n, j, sorry. Probably I should have used k. I regret my j. But anyway, there it is. So I'm just going to, basically that's just this 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 4 factorial, which is 24. So that's the fourth Taylor polynomial. Now the remainder, that's why we call this R, remainder. It's the difference between this and that. That remainder, let me write it down, it's the next term. So in this case, we're talking about the fifth term. So I'm going to use, first of all, the fifth. So f, I'll use a little Roman numeral v. So if that's okay. The fifth derivative evaluated at some tornado divided by 5 factorial times x minus 0, because this thing is centered at 0, by the way. 0 a equals 0 or x0 equals 0, however you want to call it, to the 5th power. Hold on a sec, we're almost there. Remember, x is 1/2, we're going to get there. So I need the fifth derivative. I need the fifth derivative of e to the x. I think you all know what the fifth derivative of e to the x is, but just in case, let me write it down here. The fifth derivative of e to the x is e to the x. Next thing I need to know is I need to know worst case scenario. What's the worst? How big? How big could this be? E to the x be between x equals 0 and x equals 1/2. So that's the big question. What's the worst? What's the biggest? Because that's what I'm going to use as a stand-in. You see, the remainder, the difference here, the mean value theorem says that some point exists where this works, but I don't know where that point is. And so instead of saying I know where the point is, what I'm going to do is I'm going to hedge my bets, and I'm going to get the worst case scenario. What's the worst? What's the worst that we could have happen? The worst is x equals 1/2, right? Because you know what e to the x looks like. It looks like this. It's an exponential curve, and 1/2 is the biggest. So the worst case scenario is x equals 1/2, and so that's what I'm going to use. So let's do that. So this is going to be less than or equal to, I suppose, e to the 1/2 over 5 factorial. Oh, what am I doing? I don't know. 5 factorial times 1/2 minus 0 to the 5th. If I was evaluating this at a different point, I would have a different number here, and I'd have a different number there. Okay, so this is sort of a bound. It's the worst case scenario. So let's do this on a calculator. I want to know. But how funny. This is kind of circular, isn't it? To know. Okay, let's pretend that we don't know what e to the 1/2 is, but we know approximately how big it is. So I don't know what it is, but I'm going to say that it's less than 2. Is that all right? So then that'll be even better. This can be less than 2. That way, it just feels dishonest to me to use e to the 1/2 in a thing where I'm approximating e to the 1/2. So anyway, yeah, it's ridiculous. But anyway, now let's do this. So we know it's less than 2 though, because we know that e is a little under 3, and the square root of 3 is 1.732. So actually it'd be less than 1.732, but this will be good. This will be good. Okay, so let's do this on the calculator. I'm going to compute this because I don't want it. Well, I could do it in my head. This is going to be what, 16 times 120? I'll do it on the calculator. So 16 times 120 is 1920. So that is 1 over 1920, which is approximately 0.0002. Wait, is that right? Hold on. No, that's a 5, isn't it? Yeah, this is my brain having a problem. Yeah, it's 5. Sorry, a 5 there. 5. Close enough. Here, let me get rid of my 2 and my 5. 5. Okay, so I'm within 0.0005 of the truth according to this. And remember, I kind of hedged my bets here, and this whole thing is hedging my bets. So that's how close I can be 100% sure that I am less than that away from the truth. And in fact, when you go back and you look at the numbers, what was it? It was, look at this. The truth was this. Here's what I got. I'm actually within 0.0002. No, sorry. I can't add. 4. 0.0004 if you compare the truth with my approximation. I'm pretty happy with my remainder. It was pretty darn close to the actual difference here. So this is just a way that we can approximate how close, if we add up a bunch of numbers and stop, how close can we expect to be to the truth? We can use this remainder theorem. Where is my remainder theorem? There it is. And we will use this more in your homework. I don't know if it's today's or Monday's homework. I think I may be ahead by a day. It doesn't matter. You could probably do, I don't know what today's, yeah. We'll figure it out on Friday. Also, the practice test is just last year's test. It's already online. You can go look at it if you want to. And